We have Willem Vermost and Pavlo Kondratenko, who are good friends of mine. We spent a lot of time together in Wuppertal. Willem works for VRT, Pavlo works for the EBU, and these guys really know a lot about what's going on with 2110 testing, and they're going to be talking about PICS and the new SMPTE recommended practice 2110-25, which hasn't quite been published yet, but it's getting close. So some really interesting information on testing and how things are going to go forward. So take it away, Willem.
Well, thank you, Wes, and thank you everyone here in the room. The new era of 21 testing and with PICS, not with a G, with a C, and RP 2110-25. What is it about? And why are we talking even about this? Well, actually, it started all probably even before the first JTNM tested program. So this is the driver of the rest of the presentation. So maybe you know, but just to be sure, what is the JTNM tested program? It's not a certification program, it's just a snapshot in time of the current state of the industry. I'll leave the wall of text there, you don't have to read it, it's for your afterthought. Now, the tested event looked a little bit like this, with, I think on the screen you see now 30 people who did run the tests. That's an incredible deal. If you'd like to scan the QR code, you can download the tested catalog with the tested results as well. So the tested results, they look like this, and the catalogs, they look like that. Please don't delay, just download them straight away. So what's important to know? The road towards the tested event. While drafting the standard, and that's, well, even before 2017, remember IBC 2017-2110 was really published. So before this, there were dirty hand events. And always people come together, many manufacturers come together, they try to see how the standard already works, interoperates, and with the feedback, they come back to the drafting committee in SMPTE and they discuss whatever that needs to be changed. Of course, when a process like this is going on, test manufacturers are in the room as well, already with test equipment, moving through the whole process as well. That's normal, this is how it goes. We need to check the theory in real life and then get back and maybe change the theory a little bit. So then we had an IP showcase with a huge technology demonstrator here at IBC 2017. The 2110 was published, and then the next step, it's a published document. So it's not just a technology demonstrator, we're moving into real products. So that's a real change. So then we started at the tested event to dig into specific parameters, and we asked test and measurement vendors with their kit to come in. And of course, all those vendors have similar things to measure. That seems pretty obvious. Some of those things are pretty basic, some things are pretty advanced. So we did try to perform a set of tests. And now actually thinking about this, you can imagine two problems popping up. While test equipment is being built while the standard is being made, the nomenclature is not clear yet. And maybe all the things, the formulas they use, they're already in the kit. And by the end of the day, if you start to compare the same measurement, maybe kit A or kit B has a different name for the same measurement. Maybe a different formula. And maybe it's just the plus or the minus that's changed, right? So it could be a very simple thing. There's also a second problem, and this is why I've brought Pavlo here, because he's the genius behind creating the PICS document. Whenever you start to discuss something about the standard, is it really mandatory? Do we need to have it? Or it's maybe you should have it. Even coming together with experts to discuss, it seemed not that obvious. So we needed something to verify and to clarify what's really mandatory and what's not. So Pavlo will take this part just after problem 1. So the first problem, I actually told you all the text you can read here, so I'll skip to the next slide. And it's actually as simple as this. When you're at home and you try to measure the voltage on your circuit, well, you take your voltage meter, and whether you do it in the Netherlands, you do it in Belgium, France, or you do it in the States, or maybe in China, it's always called volts. The measurement unit is volts. So you can compare it. And actually, I thought, well, probably we need something similar. If we're doing measurements in 2110, maybe we need to clarify the nomenclature. Because during the tested event, we were talking about, oh, I am measuring this concept. Somebody else said, well, that's pretty strange because the thing you mentioned, that's a theoretical thing in the receiving device. You cannot measure this from the outside. And I started thinking, and of course the guy was pretty obvious, he was right. So we needed something else to start to discuss. So we needed agreements about the measurement, the nomenclature, and also some formulas to be the same. And this is why the title of the slide is called Avoiding the Babylonian Speech Confusion. And this is the only thing we had to solve, which is a simple problem to solve, right? So we're talking about senders, the network, and the receiver, and all the specific parameters. And I won't bore you with all the specific measurements, but just a few to give you a hint. So this is a schema I would like to bring into the presentation here to talk about what we are measuring. It's maybe a little bit small. I don't know if you can see the details in the back of the room. So let's try to make it a little bit bigger. Voila, there we have it. So the middle graph here shows actually something which is written in -21 of the standard. And the example here is the gapped read shuttle. So if we were talking about, we will measure the packet read shuttle and the gapped read shuttle, and we are talking about TR and the TR numbers, that's the time you read out packet 0, for instance. This is something you cannot measure. This is within your receiver. The thing you can measure is when a packet arrives at your receiver, measuring as close to the receiver as possible, or measuring as close to the sender as possible, which is described in -21. So on top you see the packet arrival time. In practice, that should be a copy of the middle graph, right? So the packet arrival time, that's the first concept that we thought this could be helpful. It's just a name change, but actually it helped a lot during the discussion. Packet arrival time. Now at the bottom you see something that we'll dig into later on. Because packets are arriving at the piece of kit, so packets are stored in a buffer, and that's the lower part. You see, a packet arrives, then you see the graph is going up. So this is representing the virtual receive buffer. And the moment the packet read shuttle kicks in, the packets are read out of the buffer. If everything is in balance, you see a perfect ±1 wiggling of the virtual buffer. Now, all those pretty things here on the graph, they do have names. And actually, I thought we were measuring TR offset, but you cannot measure TR offset. This is an offset time when the reader starts to read the packets. So what we can measure is actually the first time the packet arrives. FPT, we call it now. That's there on the top, FPT. And when talking to vendors, on the multiple devices, there were a plenitude of names. There was video timing, video to PTP, PTP to video, first packet timing, first packet offset, stream timing. All names which are probably plausible, but if you have different pieces of kit in your lab and you need to compare those things, I think this is not a sane option, right? So we need to come to an agreement what name we shall use for this type of measurement. In this case, I think, and this is temporarily because the document is not out, we'll go for first packet time. Now, another part of the equation, it's the equation. Some people say, no, it's actually first packet time is n times t frame minus the arrival time of the first packet. Well, it's probably a stupid example, but you can imagine there are a few formulas just flipped backward. So this would also be strange if you're going to a tested event or you're qualifying your kit at home and one measurement kit says minus and the other one says plus. Who can you trust? So it's not just about nomenclature, but it's also for the user, the end user, to get some more trust into the standard that's actually working pretty well. So a few other examples about TR offset and those sort of things. I won't bore you with it, but you can imagine that there are different namings and different formulas in the document. Maybe to speed up a little bit the discussion, of course, we can talk about the virtual receive buffer, NC max, and that sort of things. So whenever packets are arriving up front, you're storing virtually your packets in a buffer before you start to read. Now, there was a plenitude of names as well, the buffer model prefill, the buffer margin, the buffer target, and would you like to express it in a number of packets or maybe in an amount of time? All discussions. Luckily, we're through with these discussions. Now, that's about formulas, but you can imagine that some things are not just formulas. At some point, you need to have something else. You need to have even full algorithms. And when we get into the algorithm space, things might be a little bit different because everybody has its own way of creating the algorithm. So even for the measurement of C, which is the model that describes how good your piece of kit is with a network in order to be sure that the network doesn't drop any packets in the network. There's the C buffer model. Now, we even described a potential algorithm how to measure C. Now, comparing measurement kit, there's no problem at all with C. The C buffer model seems to be implemented in every piece of kit in a similar way. This is actually the most mathematical interesting way to solve it. It's pretty easy and straightforward. Now, thinking about VRX, the virtual receive buffer, that's completely another beast. And I think we're even discussing a little bit, and at EBU we created the two different models that we were discussing. Because if you think about a gapped packet read channel, there might be zones of interest where you need to look at. Maybe the zone where the packets are really thriving through the network, because in the gap, there's nothing going on. And maybe you want to know what's the minimum of your VRX during that active zone. So there are different ways of looking at the same problem. And this is even how we described it. We defined the two models in EBU list, and we were looking at the differences. So this is why actually today, if you have measurement A from kit A and kit B, you probably can see minor differences in the results. This is normal, but by the end of the year, when we have this document, let's hope we get rid of those differences. So no formulas, but algorithms, and that's more fun, at least for me. Maybe I'll skip through those details. And of course, moving through a tested event, we already tweaked EBU list to be conformant upfront with what will be in RP-25. So probably I've bored you enough with formulas and theory. So maybe I'll give the word to Pavlo to talk about the PIX effort he's doing.
Thank you, Willem. So just to remind you, the idea of creating PIX for the whole family of ST2110 standards probably came up after some endless discussions during the first GNTM tested events, whether some specific requirement was really applicable or not applicable to one certain implementation. And sometimes it's easy with these questions, like some requirements in the standards are only applicable to the senders. So if you have a receiver-only device, then it's certainly not applicable. With other requirements, that's not as straightforward. And especially when some device failed the test, that was verifying one of the requirements, if it was properly implemented, then suddenly it was claimed that that requirement was not applicable. And there could be a way to avoid such discussions. And well, that's of course not the only problem that PIX solves in general, but that's one of them. So what is PIX? PIX stands for Protocol Implementation Conformance Statement. these types of documents are widely used in IT. In general IT, they came up with this concept in early 90s. Just as an example, each Ethernet standard has PICs. It's mandatory for each Ethernet standard to have PICs. In media production over IP world, the first standard to get a PICs was AES67 in its 2018 version. We use this PICs as an example. We did some things differently, and well, I will tell you more about it. So, it's rather simple concept. It's basically just a checklist of requirements, but you can use it also to provide more than just that. So just providing this checklist, we hope it will help implementers to, for example, not oversee some specific requirement, just lose track of it. We will ask the implementers to fill in this checklist, this pro forma. For example, for each subsequent JTNM tested event, that will be the first step when applying for a test for their device. Also, we try to use this occasion. There is a work group of industry experts working on the documents. So in general, standards are rather complex documents. Sometimes it's not quite easy to understand them. So where we find it useful, we try to add some clarification to some specific statements, some specific requirements of the standards. So that would be a good occasion to do so. Another thing that it tackles is every standard has some optional requirements. And sometimes it's just a feature that you may implement or may not implement. Sometimes it's several options that you can choose from. Like if you go option A or option B, for a user, it would be very nice to know which exact option was implemented or which exact optional requirement was implemented or not. Sometimes you wouldn't find this information, for example, in the datasheet of a specific piece of equipment. In the end, we hope that it will help achieve better interoperability between devices, between implementations of the same standard. We think that it would be a very good idea to use it in procurement process. So before purchasing some piece of equipment, the user might ask the vendor or the dealer to provide the filled-in PICs pro forma and get better knowledge of the equipment you are going to use. And of course, that's what I started with, we will use in testing, so in our JTNM tested events. PICs, there are two formats where PICs documents normally come in. It can be a separate document or it can be an annex to the standard itself. So for example, in AES67, it's an annex. For ST2110 PICs documents, it will be a separate document. It will come in the form of recommended practice. It will be also a 2110 document, and the number after dash will be the same as original document. It is 4, but plus 100. So PICs for ST2110-10 will be recommended practice 2110-110. So the first thing we do in PICs is we take every requirement and we assign a requirement level. So you know in every standard there is a conformance language, and it designates if each requirement is completely mandatory. In SIMT that's keyword shall. If it's a stronger suggestion, it's should, or if it's optional, then it's may. And well, at the bottom of the slide, you see how the actual pro forma looks like. We give each requirement of the standard a number. That's already useful if you need to discuss this specific requirement. The second column is the requirement itself, taken from the standard as is. Then that's the requirement level. So you see it's red. The first one is red. It means that it's mandatory, but we also differentiate between requirements that are mandatory for each and every implementation and those that are mandatory only for a subset of implementations. And I will show you how we differentiate and how we got away from this not applicable thing that is, for example, still there in AS67 PICs. The fourth column, we called it nodes. Basically, it provides the guidance to the one filling in this PICs pro forma, and also if we think that we should clarify this statement a bit, that's the column we use for that. The last column is where you basically mark if this requirement is supported or not, if it has been implemented or not. So this is how we deal with those requirements that are not applicable to each and every implementation. So we give it a pinkish color. It's like still red, but not as red as the red one. So we are asking a specific question. So this is an easy one. This is a sender-only requirement. So we ask the question, does your device, your implementation, has one or more senders? And if it does, then it applies to your implementation. If it does not, it doesn't apply, and you can just go on and to the next requirement. So, Willem, would you like to conclude our presentation?
Yeah, as a conclusion, it looks pretty simple and obvious what we were just discussing, but actually, I think it's months of discussion in order to agree what's the name, what's the formula, and what's mandatory or not. So, nevertheless, people think this is just normal and you go away and it's like this. It's not. And I hope with these, the PICs documents and -25, we could actually run a very better JTNM tested, and hopefully we can create a little bit more trust in the industry, because we're looking at the same things and now we can start to talk about the same things. So this is what I would like to conclude with, Pavlo, is if there's anything else you would add to the PICs work?
Maybe one thing to notice, PICs is not published yet. 7 documents are ready. They're in different stages of approval process in SIMTI. I hope that first ones will be published this year.
Well, thank you very much. Do we have any questions from the audience?
Could you just put up the slide again that shows the relationship between the ST number and the RP number?
Yeah, it's 100.
So 2110-10 is 21, the RP for that is 2110-110.
So it will be 120, 121.
Yeah. So if it's 2110-20, it would be 2110-120. Yeah, there's a lot of ones.